You got that? Okay. All right. So the big things here, guys, are knowing the difference between the components of climate. Okay. Remember that the components of climate are temperature, precipitation, light, and wind. Okay. So when we're describing the climate of an area, those are the four things that we describe. Most of the time, it's just temperature and precipitation. Okay. But certainly light and wind are factors, are components of that as well. Okay. It's important to know those four things because those are the four things you're going to want to describe if, for example, on a unit exam for Unit 4, I was to ask you, describe the climate of some place. Okay, I make sure it was someplace you're familiar with, but you would then describe to me, okay, like, okay, this place, is very warm. The average temperature throughout the year doesn't change very much. It's usually around 25, 30 degrees, and you talk about the temperature, and then you say this place is also quite wet. There's a lot of precipitation there. Comes always in the form of rain. It doesn't get any snow. Okay, because this place is close to the equator, the duration of daylight and the quality of daylight do not change significantly throughout the year. And finally, because it's close to the equator, the prevailing winds are from the east, and they typically do this. Okay, so you would make sure you talk about all four components of climate. Okay, now the other part of a question like that might be, okay, and some of the things that I mentioned in there, the factors that affect climate. Okay, I mentioned several times that it was close to the equator. Okay, because latitude affects climate. I mentioned that the prevailing winds typically come from the east. Okay, things like that. So make sure that when you're describing the climate of an area, you're talking about the four components, but you're also talking about how the factors make those components the way they are. Okay, that's how you make a thorough answer about climate. Okay, you talk about the factors affecting climate and how they affect temperature, precipitation, light, and wind. Everybody follow on that? Okay, that'll be important because I always ask a question like that, okay, on both the unit and final exam. Okay, so obviously we said yesterday that latitude is the biggest factor affecting climate because of the fact that the Earth is round. Okay, it's round. It's not flat. There's crazy people out there who think it's flat. Still, even though we know it's not, we have a space station that goes around and around the Earth where it's round. Okay. Yeah. Yes, says crazy people who think the world is flat. Yeah. No, because gravity pulls from the center of the Earth. Anyway, yes. So yeah, just understand, guys, that obviously we have this, the seasons, they're caused by the tilt of the Earth changing not only the amount of time we spend in the sun, but also the directness of that light, okay, how intense the sunshine is. Obviously right now we're tilting towards the sun, okay, in another, 3 weeks, it'll be the longest day of the year, and that is where we are pointed most directly towards the sun on June 21st, okay, which is, other than Christmas, like this best day of the year. It's light from 4 o'clock in the morning till 11 o'clock at night, which is awesome. But yeah, that's all coming up. Okay, and we're going to have the most intense sunlight, okay, that we receive throughout the year. Okay, altitude was also one. We talked about how as you change altitude, obviously the temperature decreases, so altitude has an effect on temperature. Okay. And we talked about distribution of land and sea, okay, nature of ocean currents. Those are all things. So if I was to make this question about something on the East Coast, okay, then, a place on the East Coast, you would talk about how it's, close to an ocean that's quite cold, okay, and that's going to cause, lots of precipitation, or if it's like in Florida, it could cause them to be exposed to hurricanes and things like that, okay. Distribution of mountain barriers, obviously that's one that affects our local climate fairly significantly. Okay, it's what causes Chinooks. Okay, it's what causes it to be kind of dry here as opposed to on the other side of the mountains quite a bit wetter. Okay, things like that. So that would be one as well, right? And then we talked about pattern of prevailing winds. It's one I brought up in my answer when I was talking here just a minute ago. Okay, centers of high and low pressure is not one that's usually very important unless you live like right here or up here, okay, where it's always one type of pressure. Okay? Because for us, we know pressure changes around here rapidly. Okay, that's why we have the expression in Alberta, if you don't like the weather, wait 5 minutes, okay, because it's going to change, right? And we get those changes in pressure all the time. That's why kind of this area of Alberta has the highest prevalence of migraine headaches. Okay, changes in pressure often cause or trigger people to have migraines. Lethbridge is actually the highest per capita city in the world for headaches. Okay, headaches and migraines. What's that? It must be their transit system. No, it's just, yeah, it's the pressure thing, right? It's all the wind. I mean, the trees there grow slanted. I'm not kidding. Go down to Lethbridge sometime. The trees all grow like this, okay? Because the wind blows that way all the time, and they grow that way. Okay. Yeah. And then we're going to do the climatogram activity. We're going to start that on Friday and finish it on Tuesday. Okay. But yeah, we'll have those 2 days to work on the climatogram activity. Just remember, this is something I will ask you to do on your unit exam. I will give you a climatogram. You will have to interpret it. Okay, tell me what it says and where you think it is. Okay, based on interpreting the climatogram. We haven't talked much about that yet, so right now that might seem daunting, but it won't once we go through kind of how they work. Okay. All right. Questions on any of that stuff? All right. So that's just review, okay, from yesterday. All right, so you guys got into this one here, okay, solar energy, okay, and basically how it gets transferred and moved around on Earth. Okay, so we looked at the 3 parts of the Earth. I think you guys got through that part, right? The atmosphere, okay, and how that works. Again, you do not need to know the layers of the atmosphere. It's not something you're ever going to be tested on. Okay, we live in the troposphere. That's really all that matters. Okay. The role of the atmosphere is important. Okay, the atmosphere does a lot of things in terms of distributing solar energy. There's no part of the Earth more important than the atmosphere when it comes to the energy available to drive processes on Earth. Okay, those processes being photosynthesis, the water cycle, okay, things like that. So what the atmosphere does, okay, the atmosphere reflects a fair amount of the incoming solar radiation. Okay. A lot of it is very bad. We don't want things like X-rays and gamma rays to be reaching the surface, and they don't, thankfully, okay, because they are essentially scattered or reflected, okay, by the Earth's atmosphere, magnetic field, etc. So things that do make it through, visible light, okay, visible light gets all the way to the ground. That's important because plants use the green part of, or sorry, not the green part, they use the reds and stuff for photosynthesis. And obviously UV light can get down. That's not always such a good thing. And obviously the infrared stuff, the heat waves and things like that will get all the way through as well. Okay. Our atmosphere also does strange things with the light as it comes through, especially the visible light. And I think I talked about this in the podcast, why the sky is blue. Right. The nature of our atmosphere scatters the blue wavelengths of light. Okay. When light comes in, visible light has the spectrum, right? Roy G. Biv, right? Okay, and it scatters all the blue wavelengths of light, which is why the sky is blue most of the time. Okay, we're starting to get some of the haze from the forest fires that are going on in northern Alberta right now. Okay, you might have noticed yesterday that the sky was kind of off color. Okay, and usually when the sun sets, it's even more so. Okay, it's more so off color, and that's because when there's more of the particulate stuff, smoke and ash and stuff like that in the air, that scatters the red and orange wavelengths more than it scatters the blue, and so the sky appears to be more grayish, brownish, orange. Same with smog. Okay, if you're driving into Calgary, okay, sometimes you can see that brown layer over the city. Okay, that's photochemical smog, and it scatters different wavelengths of light, so it looks a different color, okay, that way as well, right? So that's why we see that. So the atmosphere does those kind of weird things with light, okay? But it's also important in terms of its ability to transfer energy, which I don't think you guys got to yesterday, right? The convection and conduction, okay. All right, other big thing, this, albedo, super important term, okay, super important concept. We need to know what albedo is, okay? Albedo is the reflectivity of the Earth's surface, okay? Typically, if we're looking at darker colors have a low albedo, which means they absorb a lot of energy. All right. So on a hot day, a black car versus a white car. Okay. A black car, okay, it gets hot really fast because black absorbs all wavelengths of light, whereas white reflects them all off. It stays much cooler. Okay. That's in the wintertime, we see the effects of that. Okay, in the wintertime, when all of this place is covered in snow, okay, very little of the incoming solar radiation gets absorbed because the snow reflects most of it away. Okay, and I think we talked about also that's why we throw sand on the roads. Okay, sand and salt on the roads help to do a couple of things. Obviously, the salt lowers the melting point of the ice, okay, which is important because then it can melt at like -10 even. Um, the sand helps with traction to an extent, but more importantly, it's dark. So it makes the snow darker, which lowers its albedo and allows it to absorb more solar radiation, increasing its temperature, which helps to cause the melting process to happen at lower temperatures than they normally would. Okay, so we throw that stuff on there to help darken the road. It's also why our roads are typically dark in color. All right, if you go down to California, okay, their roads are typically made of concrete as opposed to asphalt for a couple of reasons. Asphalt is dark in color and gets really hot. When asphalt gets really hot, it gets soft. Okay, and trucks and things like that will sink into the asphalt and cause ruts in the road much more easily than they would if you have a light colored concrete surface, which is more rigid, okay, and doesn't absorb and is not as flexible. Okay, so you typically don't see that as much. They build their roads so that they are more reflective, okay, in those kinds of areas. Okay, yeah, so it's all about albedo, right? A darker color is going to heat up more. You can see that in the summertime when you're driving. You can see the heat waves coming off the road because it's dark in color. Okay, so in the summertime, okay, and we're looking at this diagram here on the right. In the summertime, up to 70% of the incoming solar radiation can be absorbed by the ground. Okay, that would be the grass, and that would be the the soil and rocks and things like that, because they're all exposed. Okay, they have a low albedo, they're going to absorb a lot of the solar energy. Okay, 10% will be reflected off of like water, okay, lakes and rivers and things like that, and 20% might be reflected off of light colored objects that just happen to be on the ground, right? But we're absorbing 70% of the incoming solar radiation. Okay, in the winter time, 85 to 90% of the solar radiation gets reflected because the snow is white. Okay, less than 10%, okay, or around 10% would get absorbed, right? And that would just be because there might be a tree sticking out that's an evergreen tree, so it's dark in color or something like that. Okay, everyone with me there? All right, so this is important because it allows us to get energy, obviously, okay, and have temperatures increase, but it's also important because it allows plants to absorb the things they need, carry out photosynthesis, produce food, get food chains going, okay, and things like that. All right. So gases present in the Earth's atmosphere also help to maintain the Earth's temperature and climate. Carbon dioxide, CFCs, methane, ozone, okay, all those things are greenhouse gases, okay? And contrary to what you may have been told, the greenhouse effect isn't all bad, okay? If it gets much worse, then it will be bad, and that could be bad, okay? But having a greenhouse effect is important. Without it, the Earth would be much colder, okay? Possibly even incapable of supporting life. Okay? So having those greenhouse gases is important for trapping some of the solar radiation and allowing it to reflect back and forth multiple times. More of it gets absorbed that way, okay? Increasing the temperature of the Earth. Obviously, we don't want to get Venus bad, okay? Because if we get all the way to what Venus is like, then it'll be as hotter than the inside of an oven, okay, on the surface, and we don't want that. Okay, everybody good with that? Okay. So basically, okay, before we get to the hydrosphere part here, there are three things that can happen to solar radiation when it encounters the Earth. Okay, three things and three things only, and you need to know these three things, so you need to write them down. Okay, we call them the three fates. Okay, the three fates of solar radiation when they strike the Earth are: one, absorption. Okay, so that's the one we would ideally like to have happen. Have that energy be absorbed. When it's absorbed, the thermal energy of the Earth and then correspondingly the temperature will increase. Okay, so that's one of the three things that can happen when solar energy strikes the Earth. Okay, the second fate is reflection. Okay, so if reflection occurs, the energy just bounces off, okay, and since it's not absorbed, it does not cause any change in thermal energy, okay, so we really don't gain anything from that. It just reflects off. Okay, the third fate of solar energy encountering the Earth is conversion. Okay, converting that light energy into chemical energy. What process does that? Photosynthesis. Okay, so in other words, light hits plants. Plants do photosynthesis. They make chemical energy. Okay, that's the process of conversion. All right, those are the three things that can happen to light energy when it strikes the Earth. Okay, I have always asked a question about that on the unit exam for Unit 4. Okay, and the way I usually do that is I take a picture, like I go to Google Earth, and I just take a picture of some place on the Earth's surface. Okay, and I put the picture on the test and I say, this place is here. I tell you where it is. And then I say, talk about what happens to the light when it strikes this area, right? So you'd want to look for things like, is it covered in snow? Is it covered in jungle? Is it a dormant grassland? Okay, so depending on what you see, you can talk about how much of the energy is going to be absorbed, reflected, or converted. Okay, and that's what I'd be looking for is, can you look at that picture and say, oh, well, that's a tropical rainforest. There's going to be a lot of absorption because it's dark in color. There's going to be a lot of conversion because there's tons of plants there. Okay, so this place is going to make lots of photosynthesis, lots of chemical energy, and very little of the light will be reflected. Boom. Okay, so you talked about the three things and you analyzed how they would work in that particular area. Does that sort of make sense? All right, so those are the three fates. Does anyone still need those? All right, the hydrosphere. Okay, so the hydrosphere is all the water on Earth. Okay, and all the water on Earth is important. Okay, because the water cycle is very, very important. Okay, how many times throughout your school career have you been taught the water cycle? About 1,000,000 times. Yeah. Okay, certainly 4 times for sure. Okay, it's in 4 different parts of the science curriculum as you go through school. Okay, and that's because it's important. Okay, without the water cycle, things just would not work the way they work on Earth. Okay, we have to have water changing state. Okay, and changing state requires energy. It requires energy to vaporize water. Okay, energy is given off when water condenses. Energy is required to melt ice. Energy is given off when water freezes into ice. Okay, so we've got those processes going on. Okay, and they're pretty important. So all the water on, above, and under the Earth's surface is known as the hydrosphere. That can be water vapor, liquid water, or ice. Okay, less than 0.1% of all the water evaporated from the surface of the Earth is returned to that like particular spot, lakes, rivers, or streams, or seeps into underground hollows. Most of it ends up in the ocean, right? And that's because of what process? Runoff. Okay. If like around here right now, it's a sunny day, water is evaporating from not only the plants, but it's evaporating from puddles, sloughs, lakes, whatever. Okay, it's going up into the atmosphere. It's not going to fall back down here. Okay, it's going to move. The atmosphere is always in motion. It's going to move things somewhere else. When it rains, that stuff eventually runs into a river and is carried to the ocean. That process is called runoff. Okay, and then it ends up not here. Okay, but then it evaporates from the ocean and comes back. Okay, I mean, it's all one big cycle, right? There are, yes, places on Earth where more evaporation than precipitation takes place. Those are called deserts. Okay, and then there's places, obviously, where there's more precipitation than there is evaporation. Those are usually called jungles. Okay, and that's just kind of the way it works. All right. So the water cycle is driven by the sun's energy. Okay, so this is how the hydrosphere interact. So all the water on Earth interacts with solar energy. Solar energy causes the water cycle, okay, to occur. So we've got incoming solar radiation, and we have two processes that are caused by that. Okay, evaporation. So that is the solar-driven vaporization of liquid water from oceans, lakes, etc. And then there is transpiration, or sometimes it's called evapotranspiration. That is water evaporating from the surface of plants as they carry out photosynthesis. Okay? That can also be a very large amount of water. Okay, if we're talking about the amount of water that evaporates from a tropical rainforest in a day, okay, we're talking about millions of liters of water. Okay, that's just from the plants. All right, so those two processes, okay, in the end, they do the same thing. They put water vapor into the air, but energy is required for that to occur. Without solar energy, that process doesn't happen. Everybody with me on that? Okay, so it's really important that energy be present for the water cycle to occur. All right, that water vapor goes up into the atmosphere, and as it goes up, it condenses because it gets cooler, okay? Because temperature decreases as we go up. So those clouds, that water vapor condenses, it forms clouds, and then we get precipitation of various forms. Could be rain, could be fog, could be hail, could be snow, okay? Just it all depends on what the conditions are in that particular place, okay? But we consider precipitation all to be the same thing. It's the return of the vaporized water to the surface of the earth, okay? Now, so we got precipitation, that being kind of our third process here, okay? So we got to make sure we know the process. So we got evaporation, transpiration, okay? We've got precipitation, that's the water returning. Okay, water that strikes the Earth's surface is going to do one of two things. It could run off. Okay, if that happens, that's water flowing in rivers and streams and whatever else headed to the ocean. Okay, and then there could be this process here. Okay, it's kind of small and hard to read, but it's called infiltration. Okay, if you infiltrate something, you get inside of it. That's what's happening here. Okay, water is essentially being absorbed by the surface of the earth. Okay, it is very similar to how like water goes through coffee grounds if you're making coffee. Okay, that would be like infiltration. So it's percolating down through the soil particles, okay, and being held in the soil, or in some cases, it even ends up in aquifers. That would be underground water supplies. Okay, so if you live on a farm and you have a well, okay, your well is drawing from an aquifer. Okay, an aquifer is not an underground lake. Okay, people kind of envision groundwater being like these underground hollows full of water, and that's not usually the case. Most of the time, it is more like, just wait outside for a sec, please. It's more like if I have gravel in a glass, if I put like filled a jar with gravel and then poured water in it, the water would fill up the spaces between the gravel. Okay, what your well does is puts a pipe down into that gravel and creates a suction that draws the water out of the spaces between the gravel. Okay, it's kind of more like that. Okay, but either way, that water gets there by infiltration. So it's either going into the water or it's going into the aquifers. Okay, and then there can be storage of water in either a solid form, okay, ice, or a liquid form in lakes and streams and things like that. Okay, everybody with me there? All right, so the big thing you need to get out of the water cycle in grade 10 is not just the processes, but how energy is involved in making that work. Okay, all right, give me one sec here, guys. Okay, so just talking about kind of distribution of water here. Most of the water on Earth, 97% of it is salt water. Okay, it's in the oceans. The other 3% is fresh water. Okay, that's a pretty important 3% because that's what we as humans need, okay, in order to survive. Okay, so 3/4 of all fresh water is found in polar ice caps and glaciers. Okay, so that's not good. We only have 3%, and 3/4 of that 3% is in a solid form. Luckily for us, a lot of that 3/4 lives around here. Okay, it lives in the mountains. It lives, a place like that where it melts all the time, and we get it, and we get this nice, clean, fresh water. Okay. Problem with that is what's happening to those glaciers. Yeah, they're shrinking, and there'll be people out there who will tell you it's all our fault, but they've been shrinking for like 10,000 years. Okay? The last ice age was 10,000 years ago. Okay, and if we were standing right here 10,000 years ago, we'd have been under a 1 kilometer thick sheet of ice. Okay, so imagine that. Okay, I mean that's how the big rock got here. It got pushed out here, okay, by a big glacier as it expanded. Okay, now the glaciers are retreating, okay, and we see the effects of that. Okay, are they retreating fast? Yes, that's a problem. Okay, but the fact that they're retreating at all is not necessarily our fault. But we do have to be mindful of it. Okay, this picture here, guys, is of the Robson Glacier, okay, which is near Mount Robson, and it's quite long, but not nearly as long as it used to, okay, or as it used to be. When I went and hiked here, at the toe of the glacier, well, actually, there was a sign where the toe of the glacier used to be. It was marked, the Alpine Club of Canada marked the toe of the Robson Glacier at this position in 1901. Standing next to that sign, you are in a grassy meadow and you can't see a glacier. Okay, so in just over 100 years, that glacier has receded lengthwise several kilometers. Okay, and that's just lengthwise. What else is it doing? It's shrinking this way too. It's a three-dimensional retreat, right? Okay, this glacier that you see here used to fill this whole valley. Okay, 100 years ago, it would have been all the way up here to this ridge. That would be probably 300 meters, okay, taller, right? So they're shrinking a lot, but that's what provides us with our fresh water. It's an important part of the water cycle. Okay, we just have to be mindful that they're shrinking. Okay, this is obviously where the water ends up. Okay, it runs off in waterfalls and rivers and such. Okay, and then it ends up here. Okay, ends up in the ocean. Okay, we have 1/4 of that 3% of fresh water that is groundwater. Okay, and that's what provides the majority of drinking water. Okay, here in Okotoks, we don't get our drinking water from the Sheep River. Okay, we get our drinking water from wells. Okay, there are several wells, okay, in the area that we use to draw, and that's why we have such strict regulations on our water use. Okay, is because the wells can only produce so many liters of water per day. Okay, and if we go above that, then we will take them down below their ability to recharge. And if that happens, we could eventually run out of water. Okay, obviously we don't want that, okay, and that's why it takes sometimes a long time to get new developments going, because in order to get a new development started in Okotoks, you have to ensure that there is sustainability on the water supply. Okay, so when they made like Mountain View and the new Darcy Ranch area there, okay, that stuff all had to be approved, and there had to be studies done on the volume of water that would be used by that many people and whether that was sustainable or not. Okay, that sort of makes sense. That's also why that Windwalk one that's supposed to go across Highway 7 on the other side is taking so long. Okay, it was supposed to start like 10 years ago, but they haven't been able to get the water licenses. Okay, the water license is a big deal. All right, the lithosphere. So this is the solid part of the earth, okay? All the rocks and the soil and all of that kind of stuff, okay? So the lithosphere doesn't do much in terms of transferring energy, okay? Transferring of energy happens within the atmosphere and it happens within the hydrosphere because they're fluid, okay? They move around easily, so they transfer energy easily. The lithosphere, because it's solid, doesn't transfer energy very well. Okay, energy absorbed, in the California desert does not travel through the Earth's crust here. Okay, it just doesn't. All right, that's not an effective method of transfer. Right, but energy that is absorbed by the atmosphere anywhere on Earth can end up here. Energy that is absorbed by the ocean anywhere on Earth can end up affecting weather here. Does everyone kind of follow me there? That's kind of how El Nino works and things like that. All right, so the lithosphere is all the rock on Earth, no matter how small. Okay, most important part of the lithosphere is that it provides soil for plants to live in. Okay, so what's soil? Soil is the topmost layer of the Earth's surface. All soil is different. Okay, there are many, many different kinds of soil. Believe it or not, what you see here is soil. Okay, in this picture, all these rocks. Okay, down here, this big salt flat, that's all soil. Okay, it's not necessarily good. It's not good soil, but it's soil. Okay, it's the topmost layer. Something can grow in it. Okay, we see these like sage and mesquite bushes here that are growing. Okay, it's good enough to support plant life, so it's soil. Yep. Right. We also have to remember that soil is its own ecosystem. Okay, it contains biotic and abiotic components, that is living things and non-living things. The non-living things would be like minerals, nutrients, okay, things like that, and then the living parts would be bacteria and fungus and plants and things like that. Okay. All right. Soil's typically broken up into layers. If you ever dug a hole as a kid, you probably saw that. Okay, there's like the dark stuff on the top, and then the clay underneath that, and then there's rock underneath that. In Okotoks, it's a really good place to see that. Okay, reason for that is our soil here is kind of thin. Right, you have a topsoil layer that's maybe a half a meter thick, and then there's a kind of a clayish layer underneath that that's maybe another meter or so thick, and usually strewn about the bottom of that are rocks. Okay, if you go much lower than that, you hit just a big layer of sandstone, right? Because Okotoks is built basically on a big outcropping of sandstone, right? So that's our bedrock, that's our lowest layer, right? So we have the O horizon, okay, which is kind of just the organic material. Right on the top would be like thatch, dead grass, and weeds and things like that, okay? And then below that would be the A horizon. That's typically what they grow out of, okay? That's where you'd find the roots. B horizon is kind of the clayish part, and then underneath that is the C horizon, which is the bedrock. Okay, the other name for the bedrock is parent material. Why would we call it parent material? Yeah, okay, we get soil by bedrock breaking down, by parent material breaking down, so it kind of gives birth to, okay, the dirt. All right, so that's why we call it parent material. Okay, so this would be a typical soil horizon that you might see in our area. Okay, here's our topsoil on the top, and then this would be our B horizon here, kind of clayish, and then here's the bedrock underneath. Okay. All right, so A horizon is the topsoil. It's a mixture of decomposed rock, okay, living organisms, decaying organic matter, that would be dead plants and animals, okay, plant litter, leaves, things like that. All right, so again, the topsoil is usually the darker of the layers, okay, but not always, but usually. Then you got your clay layer, and then you got your rock underneath. Why is clay always underneath? I mean, you probably noticed you played in a sandbox as a kid, like you dug through the sand, there was always clay underneath. Okay. The reason clay always ends up underneath is the size of the particles. Okay, soil particles tend to be larger. Clay is like flour. Okay, so soil would be like having salt or sugar between your fingers. You do this and you can feel it's gritty. Okay, but if you do that with flour, it feels almost slippery because it's really, really fine. All right, so clay is like that. It's fine. So it washes down between the bigger particles and always ends up collecting underneath. Right, so we said the B horizon, okay, typically mostly clay, right? Some places there's almost no A horizon. The B horizon is right at the surface, okay, and so most of the clay is there, including the tropical rainforest. Okay? In the tropical rainforest, there's virtually no topsoil, which is odd for the number of plants that live there. Okay, but the reason that there isn't is because it's always flooded and it's always washing it away. Okay? The plants actually get their nutrients directly out of the floodwater. Okay, and then we have the C horizon, okay, which is our parent material. Okay, again, this is a soil horizon like you would see here, okay, in our area. Okay, you got the A horizon, and there's a few rocks in that. Okay, you got the B horizon here, there's more rocks in that, and then you see the broken up kind of bedrock underneath. Okay, the further down you go into that, the bigger the chunks get, the more solid it would become. Okay, now the solar energy budget thing here. What we need to talk about is, and I do have it here. Okay, so the Earth's a system. Okay, it's an open system. We talked about that in the last unit, right? Open, closed, and isolated. The Earth is an open system, so it is always exchanging matter and energy. Okay, and what happens to that energy is important. If most of it reflects off the Earth, that's bad because then the Earth will be too cold. Okay? If too much of it gets absorbed, the Earth will be too hot. Okay, so there has to be kind of a delicate balance there. Okay, so when light comes in, we start out with 100% of it. Okay, I'm just going to make that a little bit bigger. Okay, we start out with 100% of it, okay, and about 6% of it gets backscattered by the air, making the sky blue, okay. Some of it gets reflected by clouds, up to 20%, okay, and then there's some reflection by water and land surfaces, about another 4%, okay, and then coming in, about 16% gets absorbed by the water vapor and dust and things like that in the air, okay, gets absorbed by clouds, okay, and 51% of it would be absorbed by land and water. Okay. Anything that gets reflected heads back out. Okay. On its way out, okay, there can be absorption by water vapor, carbon dioxide. That would be greenhouse effect. Okay. Then there's just some stuff that gets emitted. There's emission by clouds. Okay. There's sensible heat. There's just heat coming from the earth. Okay. That stuff all just kind of goes back out. Right. Okay. So obviously, yeah, everything on Earth, okay, is powered by the sun. Okay. Basically, every food chain, okay, every living organism on Earth is either directly or indirectly powered by the sun. The very rare exceptions would be the organisms that live at the bottom of the ocean, okay, where no light penetrates. They typically have a bit different life cycles. They work on chemosynthetic types of things rather than photosynthetic. Okay. But basically everything else rides on the sun. Okay. Even your car. Okay. Your car is powered by the sun. So next time an environmentalist gets in your face, you can tell them you have a solar powered car. Okay. Even though you don't have solar panels on the car, it's still solar powered because where did the energy come from for the fuel? Yeah, plants. Prehistoric plants, okay, but still plants, okay. All of that was energy that was captured and converted by plants, hundreds of millions of years ago, and then, through the process of fuel formation, okay, it turned into other things, but that was all solar energy at one point. Okay? That's where all of the energy on Earth comes from. Okay? It's basically solar energy, either directly or indirectly. Okay? So when you eat, steak, okay, that steak and the energy in that steak came from the cow who ate the plant, who used the sunlight. Okay, it's always going to come from the sun. All right, questions on that? Okay, so how does this energy that the Earth absorbs get transferred and distributed on Earth? That's kind of the big theme of this unit, is how does it get everywhere? Okay, in order to understand how it gets everywhere, we're going to talk about the 3 methods of heat transfer in 5 minutes. I'm going to give you a 5-minute break because I've been talking nonstop since the start of class. So you got a 5-minute break, and then I'm going to go over this. Okay, so there's 3 ways that thermal energy or heat can be transferred from one place to another. Okay, some of them are really important in terms of energy on Earth or energy transfers on Earth, and some of them are less important, but we still need to go through all 3. So the first way is by what we call conduction. Okay. Heat transferred by conduction happens in solids, okay, in solid materials only. Okay. Conduction happens when you heat up, or there's a thermal difference, obviously, between one side and the other of a solid object. Okay. When we heat up one side, what happens to the particles there? Right, they move faster. Okay. Now, in a solid object, the particles are very tightly packed. That's why a solid can't take the shape of its container. The particles can't move past each other, but they can move back and forth. Okay? When they do that, they run into each other. And when they run into each other, they transfer energy to each other in the same way like billiard balls would. If you shot, the cue ball at another ball, it transfers its energy to that ball by hitting it. Okay? Also, if you've ever been like at a concert in a mosh pit, okay, people are moving around, but they're packed in like this, so they move around only a little bit, but they transfer energy to each other. Okay, that's what it would look like if we were looking at the atoms inside of a solid. They'd be tightly packed and running into each other all the time. The hotter we make it, the more they run into each other, and those collisions will slowly, in some cases, fast in some materials, transfer thermal energy from one end to the other. Because as they move here very fast, they transfer that energy to the other particles with that movement. Does that sort of make sense to everybody? Okay, which is why you don't want to use like a metal spoon when you're cooking something, right? Because metal typically conducts heat very well, right? So if I've got a metal spoon sitting in a pot of soup, okay, and I leave it in there and I come back and grab the handle, I'm going to burn myself because heat will have conducted up the handle of the spoon. Okay, it's also how heat goes through the metal part of a pan in order to cook whatever you put in the pan. Okay, it's conducting through and then making the surface hot. Okay, so that's conduction. Conduction doesn't play a very big role in transfers of energy on Earth because it only happens in solids and it doesn't work over large distances. Okay, it can work over the length of a spoon, but it's not going to work over the length of a continent. Okay, we're not getting energy, like we said before, from California transferred through the ground. Okay, it just doesn't work that way. Question? actually going to get to that here in just a second. It's made out of metal, but the design of it is what keeps the heat from transferring through. And I'm going to show you why here when I talk about convection, okay, which is next. Okay, so convection, okay, is the most important of the energy transfer processes in terms of moving energy around on Earth, okay? We typically feel convection as wind, okay? Convection is the movement of a fluid due to differences in thermal energy. All right. So in your house, your house takes advantage of convection when you run your furnace. Okay. Where are your heating vents? On the floor. Okay. Your heating vents are on the floor because hot air comes out of them, and cold air is on the floor because hot air rises and cool air descends. So we put the heating vents on the floor, okay, so that when the hot air blows through them, it's heating the coldest air first. Your cold air returns, which take air back to your furnace, are also on the floor. Okay, so cold air is going back through those and being drawn into the furnace and reheated, okay, in order to heat your house. Okay, in the wintertime, okay, what floor in your house gets coldest? The lowest floor. Okay, if you want to heat your house most effectively, you actually close vents, the heating vents in different parts of your house. Okay? In the wintertime, if you close the vents on the top floor, you'll heat up the bottom floor better, but the top floor won't get terribly cold because the heat will naturally do what? It'll go up. It'll naturally go up. In the summertime, you do the exact opposite. Okay? In the summertime, if you're running an air conditioner, you close all the vents in the basement and on the main floor, and you let all the cold air from the air conditioner go to the top floor. Okay? Because that's where all the heat is. Okay? And because naturally the cold air will descend and cool the bottom floor on its own. Okay? That can make your heating and cooling most efficient. You're taking advantage of convection, okay? Which is really just the second law of thermodynamics taking place. Okay, remember that the second law of thermodynamics is that heat transfers from hot to cold. Okay, and all we're doing is seeing that in action. That's convection. Hot air rises, cool air descends. Okay, that's just how it works. Okay, we see that in like if you've ever been to the ocean. Okay, so this would be the shore. That's a tree. That's the ocean. Okay. I'm not a very good artist, so that's why I tell you this is this and this is this. Okay, so what can happen, okay, with convection is it's kind of an interaction between a bunch of things. It's an interaction between solar energy, albedo, okay, and then this movement of air. So when the sun strikes this area, the land heats up faster than the water does. Okay, which means the air above the land gets hot. Okay, and the air above the land rises. Okay. Now, in order to prevent a vacuum from forming, because all the air is moving upwards, air comes in from above the ocean. That air is cooler. Okay, so it blows in like this. We call that a sea breeze. Okay, so in the morning, typically you get a breeze coming in off the ocean, okay, because the hot air above the land is rising, cool air is coming in, okay, and then we get essentially a convection current happening. Okay, you get this cyclic flow of air due to the second law of thermodynamics. It's hot in one place, it's cold in the other, boom, things get moving. All right, so that's kind of convection in a nutshell, but convection is what drives all weather. Okay, weather, wind, all of that is convection, and that's what transfers energy from the equator to the poles. Okay, all of that stuff. It's the most important of the energy processes, energy transfer process, sorry, okay, is this convection. Now, are there ways to prevent convection? Yes. Okay, because in some cases, convection happens all the time. It happens very easily. We sometimes don't want it to happen. Okay, like for example, we don't want energy to get from the inside of our house to the outside in the wintertime. How do we prevent that? What's inside your walls? Okay, why does that work? Anyone ever seen what it looks like? Yeah, it's like that fluffy pink stuff. Okay, well, the fluffy pink stuff is fiberglass. Okay, and it's the name is exactly as it implies. It is a ton of just mashed, intertwined glass fibers. It's like wool made of glass. Okay, Oh yeah, don't touch it because it's glass. It'll actually get in your skin and you'll get itchy and it'll break off in there and you'll have little pieces of glass fiber stuck in you. Okay. You also don't want to inhale it. It's also bad. Anyone who installs insulation wears special gloves and like a breath filter. Okay. So anyway, the fiberglass is just fibers of glass, exactly as it would imply. Okay, that are just intertwined. Okay, like almost like a fabric. Okay. Now, in between those fibers of glass are pockets of air, but they're trapped. Okay? That air is trapped in those pockets, which means it can't move. If it can't move, can it set up a convection current? No, it can't rise, it can't cool, it can't descend. Okay? And that's exactly what we want. If this is my inside wall and this is my outside wall, okay, this is hot, this is cold. Okay? I don't want energy to flow through the wall from hot to cold because it wants to do that. That's the second law of thermodynamics. It wants to go that way. Okay. If I have nothing inside my wall, if it's just hollow, okay, then air next to the wall will get hot. Okay. It'll rise and just next to the ocean, cool air will move in to replace it. And I'll get a convection current happening inside my wall that just takes the energy from my house and puts it outside. Okay. That sort of makes sense? I don't want that to happen. So I stuff my wall full of fiberglass. Now the air can't move. Since the air can't move, convection can't happen. Okay, so that's one way to prevent convection. Okay, now Liam, you were asking how does my thermos mug do that? It's made of metal. Metal's supposed to conduct heat very well. Metal does conduct heat very well. That's why always at the top you can feel the top is hot, but the bottom isn't. Okay, because this is where there's contact. Inside of a thermos, there's a vacuum. So your thermos is just a container, okay, but it's a double layered container. There's a vacuum in between where the liquid is, okay, and the outside. Yeah. So what they do is they actually suck all the air out of that space. Since there's no air in there, there's no air to move. Convection can't happen in a vacuum. So it becomes almost a perfect insulator. Okay, this is how low E windows work. If you have like triple pane or double pane windows, okay, in between the panes of glass is a vacuum. Since it's a vacuum, air can't move inside of there, and they're more efficient at preventing energy from being lost through the window. Right? That kind of makes sense to everybody? Okay, so we do a lot of things to prevent convection because convection is the #1 method of heat transfer. Okay, sometimes we want it, sometimes we don't, right? Anybody ever build a Quincy? Know what a Quincy is? Okay, so a Quincy is an emergency snow shelter. Okay, they're super easy to build. You make a big pile of snow and then you hollow it out. Okay, you don't pack it though. Okay, you just shovel snow into a pile. Right now, all the little snowflakes have all these sharp edges on them, right? Every snowflake is a little bit different. So when you make this pile of snow, the snowflakes interlock, and what gets trapped between them? Air. Okay? A big pile of snow effectively works just like a wall full of insulation. There's a whole bunch of trapped air inside the spaces between the snowflakes. So when you hollow it out and you crawl inside, you can get the temperature inside the Quincy to actually be above 0. It'll actually start dripping, okay, if you do that. I used to do this when I taught in Lloydminster before. We had a snow ecology unit that we always did when I was teaching there. And so I would wait till the coldest day of the year, be like -40, okay? And I'd tell all the kids, you got to bring a shovel to school tomorrow. And we'd go out into the football field and we'd make these big piles of snow. Okay, and then we would hollow them out and crawl inside. You wouldn't believe at -40 how fast people can make piles of snow if they think they're going to get warm. Okay, so we'd make these big piles of snow, hollow them out, get inside, and we'd have 10, 12 people inside a big one, 4 or 5 people inside a small one, and within minutes they were, taking layers off because it was already like, close to 0 inside, even though it was -40 on the other side of a layer of snow this thick. Okay, it was that good of an insulator. But the other thing snow has going for it is it's what color? White. So if I'm sitting inside, not only is my heat not convecting out, any heat I'm radiating is getting reflected back. Okay? Snow is an almost perfect insulator. Okay? That's why animals burrow underneath it in the wintertime. It's an insulator. It keeps them warm. Okay? All right, that's also why animals typically have fur, okay? Animals that have, especially that stay in the cold climates, okay? They have to have thick layers of fur or thick coats or winter coats, okay? Like right now, if you look at the deer and the like mountain sheep and stuff, they all are patchy because they're losing their winter fur, okay? The thick layer that was keeping them warm, okay? That stuff traps air, okay? It just traps air and it can't move and it keeps them warm through the winter, okay? And when you wear your parka, if it's down filled, I mean, what did you fill it with? What's down come from? Yeah, it's feathers. Okay, feathers keep geese warm. They trap air. That's their job. Okay, so they insulate. It's a good insulator. All right. So everyone understands what convection is. Okay. Third method of heat transfer is radiation. Okay, radiation is any transfer of energy by waves. Okay, so heat waves or light waves are examples of radiation. Okay, so when I say radiation, I don't mean the kind that turns you into the Hulk. Okay, not that kind, because that kind just fries you like an egg. Okay, I'm talking heat radiation. Okay, or visible light. Okay, any of those, okay, are heat transfers by waves, okay, that are going to move energy from one place to another. Okay, do we radiate heat? Mm-hmm. That's why the police can find fugitives in the dark, okay? Especially if they're using the helicopter. What do they have on the helicopter? Yeah, they have something called FLIR, okay? Forward-looking infrared. It's essentially a big camera that just detects heat, okay? So they can see all the hot objects. They stand out bright white against a black background, right? So, if somebody is just, dove into a big bush, like area where there's nothing, where there's nothing but just growth and whatever, and police can't see them in the dark, okay, the helicopter flies over and they stand out like a sore thumb, okay, because they're the only thing that's hot in that area, and they're radiating this heat away that special camera detects. Okay, it detects it like we look at a light and go, oh, that's bright. Okay, to that camera, anything hot is bright. Okay, and so they can see them no matter what else is around them. Okay, the only way you can hide from forward-looking infrared is to go somewhere hotter. Okay, that or around the same temperature as you, and then you kind of blend into it. Okay, but if you're running around outside at night, you stand out like a sore thumb because there's no way to hide. Yeah, same with animal. Yeah, I mean, you can tell, like the silhouette is obvious. Like if you ever watched any police chase footage, you can see when they release the dog, right? Because you see this white, kind of dog shape running for this person who's also hiding or running or whatever. Yeah. Yeah. Oh, did they? You can also see when they get tased. The tase wires get hot too. Yeah. Yeah. I like watching those police shows where somebody runs and they're all tough and then they get tased and they're on the ground and they're whimpering. I just think that's funny. No, wow, no. There's usually lots of cursing and swearing in those. So, anyway, so radiation, guys. Okay, radiation is anything that transfers by waves. Now, how would I stop energy transfer by radiation? Because maybe I don't want stuff to be absorbed, right? Okay, I could have a hazmat suit. Yeah. Okay, don't mean that kind of radiation. Okay, like we talked about how albedo determines how much gets absorbed and how much gets reflected. Okay, what it's absorbing and reflecting is radiant energy or radiation. So if I want to prevent absorption by radiation, what color do I need to make things? White. Yeah. Okay. Light colors or shiny. Okay. Shiny will also reflect more of that away. Okay. Then that's going to prevent the absorption of radiant energy. So radiation has to be absorbed or reflected. Okay? If I want something to heat up quickly, then I want it to be dark in color. Okay. So if you're building like a solar water heater, okay, like I don't know if you guys have seen this, they have these like camp showers now. It's a black bag. You put this black bag full of water in the sun, and then it heats up from the sunlight because it's black, and you can get like a hot shower by hanging it from a tree. Okay, yeah, it doesn't work in the winter, but I mean it still works a little bit. I mean but it's going to freeze because it's minus 40 outside. But yeah, if you're building a solar water heater, you basically want to have as much water as possible running through dark pipes that are exposed to the sun. Okay, because then they're going to absorb the energy, okay, and heat up whatever is inside. Okay, This is also something that they do on the inside of thermoses. Okay, the inside of the thermos is reflective. It's silver, and it's usually polished. Okay, at least at first. Okay, so it reflects the heat back in. Okay. How many people have ever baked a potato on a barbecue? Okay, what do you wrap it in? How do you wrap it? Yeah, you wrap it so the heat goes back inside. But if you guys shiny side in, shiny side in. Hang on. This is something most people don't know, believe it or not. I know this because I've gone to a lot of barbecues and I get angry. Okay? Look at this side of the tinfoil. Shiny, polished, dull. Most people don't. I'm telling you this so you won't be embarrassed later. Okay? Guys, what I see when I go to people's barbecues is that people don't know this. Okay? And so what they do is they wrap the potatoes randomly. Some of them with the shiny side out, some of them with the shiny side in. I want the dull side out. Why? It absorbs the energy, and any energy that goes into the potato goes through the potato and hits the shiny side because it's wrapped like this, and it reflects back and forth and cooks the potato fast. If you wrap it with the shiny side out, you are going to eat a raw potato 2 hours from now because it won't cook. Okay, so what I do is I go up to the barbecue and I go, I want that one because I look for the one that's wrapped the right way. People don't know, and then they get a raw potato later because they don't realize that there's two sides to tinfoil, and it's designed that way because it's supposed to absorb radiant energy and then keep it from escaping out of the potato. Okay, so always wrap something if you want it to cook. You want to wrap it shiny side in, dull side out. Okay, if you want it to stay raw, then you wrap it the other way. I don't know why you'd want to do that, but okay, in case you did. All right, so anytime you cook something using tin foil, now you know there are two sides to tin foil. Okay, it's designed that way on purpose. Okay, wrap it the right way. Okay, now here's how I usually test these concepts. Okay, I give you a real world situation and ask you, in this situation, design something. Okay, so maybe I ask you to design a building that could keep frozen foods cool in California in the summer. Okay, so you would want to talk about, how you prevent radiant energy from being absorbed. Okay, lower the albedo. Okay, how would you insulate it? How does insulation work? Why does that keep the cold air inside? Where would you put the refrigeration unit? Okay, would you put it on the roof? Would you put it on the bottom? Where would you put it? Okay, things like that. You would want to talk about, okay, here's what I understand about heat transfer, and here's how I would prevent it. Or maybe I ask you, how would you make this thing get hot in a hurry? And you would, do the opposite, right? Or I might show you a structure and say, how does this structure work? Okay, like, here's a Quincy. Why is this Quincy keeping people warm? Okay, and you could talk about, how the snow is an insulator, why it's an insulator, things like that. Talk about the three methods of heat transfer and how they work. Basically, anything that will prevent convection will also prevent conduction. Okay, you can prevent conduction by making sure heat has to go through anything not solid. Okay, because conduction can only work through solids. Okay, that's actually how home inspectors will determine how well built and insulated your home is. They put a infrared camera and they look at your house. They can see where the studs in your wall are. Okay, because the studs in your wall will allow heat to conduct through because they actually contact both the inner wall and the outer wall. Okay, that's not, the insulation is between them, right? You have to have those studs to support it. Okay, but you can actually see where those are if your house is not well insulated. Okay, making sense? Those three methods of heat transfer? All right. Okay, when we're talking about the transfers within the hydrosphere, okay, so hydrologic transfers, water condensing in the atmosphere and then or evaporating and condensing causes the transfer of this stuff, okay, latent heat. Okay, everything we've talked about up until now is about sensible heat, okay, that's heat we can feel. Latent heat is not heat you feel. Latent heat is the heat involved in changing the state of something, right? So melting ice or evaporating water or condensing steam back into water or freezing water into ice. Okay? what's going to burn me worse? Liquid water at 100 degrees or steam at 100 degrees? Why? They're both 100 degrees. Why does one burn me worse? Nope. Nothing to do with surface area. Okay, well, let's say I get steam right on my arm, or I get the equivalent amount of water poured on my arm for whatever reason. Okay, steam burns me worse. They're both the same temperature and it's the same amount of water. Why does the steam burn me worse? The answer is the steam has more energy because it has this. It's absorbed a ton of energy in order to change from a liquid to a gas. Water's still a liquid. So even though they're both 100 degrees, they're the same temperature. Steam has more total thermal energy. And as soon as it hits your skin, it condenses back into a liquid and releases all of that extra energy. Okay, and we're talking about a lot of extra energy. Okay, if we look at what we call the heating curve of water, which we'll look at later in the unit. Okay, if this is 100 degrees here, okay, this is 0 degrees here. Okay, so water at 100 degrees has this much energy. Okay, this axis here is energy. Okay, so water at 100 degrees has this much energy. Steam at 100 degrees has more because I've had to convert it from liquid to gas, and that takes an incredibly large amount of energy. Okay, this is why when we get storm systems that move up from other places, they bring a lot of energy with them because they're bringing water vapor. Okay, they're bringing water vapor that's evaporated elsewhere. So the energy has been taken from somewhere else to turn it into a vapor. Then it comes here, condenses and falls as rain. And when it condenses, it brings that energy to us. It's what we call latent heat. It's not sensible heat, but it's energy. Okay, and it can bring that energy to us, okay, through a weather system. Yes, that's how sweat works. Yeah, yeah. Okay. So in order to cool ourselves, okay, like when we sweat, sweat keeps us cool because the energy that evaporates the sweat comes from us. Okay, and to evaporate 1 gram of sweat takes 2,260 joules of energy. Okay, so it's a lot, right? So you get out of the shower and you're wet. Okay, you get a chill almost right away because that water is evaporating off of you and it's getting the energy to do it from you. That's why you feel cold. Okay, if you're sweating and you start moving around and the sweat starts to evaporate, you feel cooler because the energy to evaporate the sweat comes from you. Okay, that's why we typically get flushed as well. If we're working out or whatever, right, the blood all goes to the surface of our skin to help cool it faster. Okay, and it evaporates off, and then we feel cooler as a result. Okay, that's all because of this idea of latent heat. So latent heat is part of how the water cycle can transfer energy from one place to another on Earth. Okay, it can move. What energy can move by convection? Okay, it can move by radiation, but it can also move through the water cycle as latent heat. Okay, so like if we're talking about the biggest energy transfers, okay, we would have convection. Latent heat would be second. Okay, radiation would probably be third. Okay, if we're talking about energy that's already on Earth, okay, obviously energy that comes to Earth comes in that form. That's how we get it. Okay, but once it gets here, latent heat would be the second largest energy transfer behind convection. Okay. All right. Okay, and then obviously within the lithosphere, the role of the lithosphere is not about transferring energy, it's about converting the energy. Okay, it's about making a place for plants to have nutrients so that they can convert light energy into chemical energy. Okay, because like we said, the only thing that the lithosphere can do is transfer by conduction, and that's just not efficient or working over long distances. Okay. So yeah, lithospheric transfers are about conversion, right? About photosynthesis. All right, questions on that? That's a long one, but we're through it. Okay. Tomorrow, I'm probably going to talk about wind patterns and things like that. Friday, like I said, we'll start the climatogram activity. Monday will be your unit exam now, okay, and then Tuesday we'll finish the climatogram activity. Okay, so that's what's kind of coming up here, okay, into the first week of June.